Hi everyone, welcome to this week's lecture video. This week, we're going to talk about three things: support vector machine, decision tree, and neural network. First, let's talk about the motivation. Suppose we need to classify the blue and red points, which has a 1D distribution like the left plot. We don't know where to put a single linear cut to separate them. Or if we want to predict the value of the vertical axis based on the value of the horizontal axis, but the distribution looks like the one in the middle, we don't know how to fit it with the line. Or if the events have a 2D distribution like the right plot, which is clearly not linear separable. So LDA or linear hypothesis don't seem to work. How do we perform nonlinear classification or regression? We need fancier machine learning algorithms then. This week, we'll learn about three kinds of such algorithms. So there are three parts of the lecture. In part 1, we'll introduce support vector machines. Then in part 2, we'll talk about decision trees. Finally, in part 3, we'll start to dive into the world of neural networks. So let's start part 1, support vector machine. We'll start by looking at a simple case. Suppose the signal events, the red dots, and the background events, which are the blue dots, have a 2D distribution like the plot on the slide. Surely they can be separated by a line. In fact, all three lines on the plot can be used to classify the red signal dots and the blue background dots. So which one should we use? If we use the leftmost line, like the one on the slide, then the line will classify the test sample represented by the black dot as background because it sits on the same side as the blue dots. However, this doesn't make sense because the black test sample is closer to the block of red signals. Similarly, if we use the rightmost line as shown on this slide, then a test sample like the one on the plot will be classified as signal despite being closer to the background events. So clearly, the central line is the best choice. This is a line that has the maximum margin, where the word margin means the shortest distance between the observations, meaning the dots, and the threshold, meaning the line we use to classify. This is called a support vector machine or SVM. This is because the line, or when more features are used, the hyperplane with the maximum margin is determined by the data points which lie nearest to the hyperplane. These points, like the two dots highlighted on the plot, are called support vectors. Therefore, the goal of the SVM is to divide the categories with a gap or margin that is as wide as possible, as illustrated by the plot on the right-hand side. But there are often outliers in the training data, like the highlighted blue dot on the plot. It is a black background event which somehow lies closer to the signals than other background events. When there are outliers, choosing the line with maximum margin based on support vectors will end up with a line that classifies the test sample on this plot as background, even though it is closer to most of the signal events. So instead of a hard margin, we choose a line with a maximum soft margin by allowing a little bit misclassification, like the line on this plot. It will misclassify the outlying blue dot as signal, but its prediction for the black test sample makes more sense. So the model is less sensitive to the outliers in the training data. The amount of misclassification can be represented by the distance, c, from the correct boundary, and therefore a regularization term, c times the sum of ci for each feature I, can be added to the SVN fit. C is then a hyperparameter to be determined. As promised, SVN can be used for a nonlinear separation, like separating the red and green dots on the 2D plot of the upper right figure. And SVN transforms the data with a kernel trick, such that when data are plotted in a transformed feature space, it looks like the 3D plot of the lower right figure, and the SVN classifier can find a hyperplane that separates them in the transform space. Some common kernels include the polynomial kernel and the radial basis function or RBF kernel, which is basically a Gaussian. You can also specify the coefficients of the kernel functions, such as the degree of polynomials you want to use. Now move on part 2, the decision tree. The concept of decision tree is quite simple. You ask a series of yes-no questions and separate the data based on the answers. For example, if the distributions of two kinds of events, the blue dots and the red triangles, look like the plot of on the x2, xy plane on the right-hand side, we can classify an event by first asking whether its x1 value is larger than certain threshold C1. If it's smaller than C1, then there's a pretty good chance that this is a red triangle. If xy is larger than C1, we further check whether S2 is larger than C2, and it's more likely to be a blue dot if that is true. Otherwise, we classify it as a red triangle. And this is a decision tree we built to classify the blue dots and red triangles. Here we introduce a bit of jargons. The starting point of the decision tree is called its root, and usually we use the feature that is most effective in separating the events for the root. The ends of the tree are called leaves. Leaves are the point where we make the final verdict on which category the event belongs to. Each intermediate checkpoint is a node. A decision tree is easy to train but prone to overfitting because in principle we can keep splitting the nodes until every training event is correctly classified. Therefore, we usually need to specify parameters such as the maximum tree depth, minimum samples used in the node, or the maximum number of leaves in order to prevent overfitting. A useful extension is to use an ensemble of decision trees, which makes the model more flexible or easier to generalize to new samples by combining many trees and take the average output. One way is to build a random forest, which means we train a set of trees by randomly selecting features and samples, and the outcome is an output which gets most votes by the trees. Another way is to build a boosted decision tree, which means we train n models in sequence, meaning one by one, and give more weight to wrongly classify events each time we train. The output comes from weighted votes from each model. Now on to part 3, the neural network. Neural network is the short name for artificial neural network, which is a model that tries to simulate the functions of biological neural networks. The plot on the right-hand side shows a simple neural network where each circle is a neuron. There is an input layer with 2 neurons. Each connects to 3 out of the 4 neurons in the middle hidden layer. And all the 4 neurons in the hidden layer connect to the single neurons of the output layer. We can have multiple neurons for the input, the output, and the hidden layers. Also, we may have multiple hidden layers between the input and output layers. Let's first discuss how a neuron works. A neuron works like a switch. In the sketch below, the red neuron takes the input from the two neurons in the previous layer and sums over the inputs x1 and x2 with different weights w1 and w2, which reflect the importance of each input. Then it adds a bias term b, which serves as a threshold value for this neuron to be activated. And it feeds the information summed wixi plus b into an activation function denoted by sigma z to get the output. The shape of a typical activation function looks like the one shown on this slide, which looks like a smooth line with two states on and off. Let me add a word on the information flow in the neural network. If the neural network processes the information only in one way, from input to output without any loops, then it is called a feed-forward neural network. We'll focus on feed-forward neural networks now. Later in this course, we'll talk about recurrent neural networks, or RNN, which is non-feed-forward. How do we train a neural network? The goal is to find the optimal weights and biases which minimize an objective function, which we'll call a loss function in the following slides. A typical choice of loss function is the mean square error, or MSE, the sum of the squares of the difference between the current output value and the true value for each training sample averaged by the number of samples. If we need to optimize a lot of weights and biases, we need a smart algorithm to do so, like the method of gradient descent, where each iteration takes a step in the opposite direction of the gradient at the current position. So we calculate the gradient of the loss function average over the input data. However, when the size of the input data is large, the calculation can be really slow. A common solution to this is to use a random subset of input data to approximate the gradient of the loss function. This subset is called mini-batch, and the method is called stochastic gradient descent, or SGD. A related jargon is epoch, which refers to one cycle of training through the full entire training data set. Training a neural network usually requires quite a few epochs. There are many things you need to decide when you train a neural network, like number of hidden layers and number of neurons for each layer, which activation function to use, which loss function to use, how to minimize the loss function, etc. We'll mention a few options below. For the activation functions, two common choices are the rectified linear unit, or ReLU, shown on the left plot, and the soft class function plotted on the right-hand side. Training with the loss function MSE can be slow sometimes, since its gradient depends on its first derivative, or slope. One may run into a region where the slope is small, so it takes a long time to reach the minimum of the loss function, and thus slow training. Therefore, another choice of loss functions is the binary cross entropy function. The formula is given on the slide, and the point is its gradient is no longer depends on the first derivative. We also have different options for solvers, meaning algorithms for minimizing the loss functions. Stochastic gradient descent is easy and useful, but there can be problems for SGD like slow training. There are many other options like add-on, which increases the step size called learning rate when the gradient becomes smaller, or LBFGS, which is an algorithm that finds the minimum using quasi-Newton's method. We can apply regularization techniques in neural networks. As usual, we need to be careful about overtraining like the situation shown on the plot. While the loss function is reduced further with more epochs for the training sample, the value of the loss function saturates at some point for the testing sample, which is a sign of overtraining. We can add an extra term to loss function that is proportional to the absolute values of the weights, called L1 regularization, or the sum of squares of the weights, named L2 regularization. You can see they are exactly the same things as the ridge and the lasso regressions we've seen before. Another method to avoid overtraining is early stopping. Many packages include the option of an early stopping, meaning we stop training when the model stops improving, either after a certain number of consecutive iterations or with a validation sample. To summarize, to go beyond linear classification or regression, there are many machine learning algorithms we can use, like support vector machines, decision trees, and neural networks. For each algorithm, we need to choose many hyperparameters or method to use. We usually tune or determine these parameters by validation samples. That's all for this week. Until next time.